Okay, so I'm getting things set up. Is there a good time that works for people? I figured I could do. So of course I have private office hours. If people want to talk privately with me, that's fine. And I will chat. But I also thought it'd be nice to have like just kind of a review session or like a homework workout, that kind of a thing. So so is my regular office hours are after this class. Does it work for people or no? How many people does that time not work for? That's a good number. Then
Recording in progress.
so that's a bad idea. Okay, well. All right, so I'm really worried. I'm mute here. So what I I get this, okay. But I guess I'm a little worried if people can't hear me. How do I turn this sound off? Huh. Hopefully some sound will come through. Okay. So good. Glad I got that talked about. So I'm going to say 3:30 Fridays. Let's call it a problem sessions. We'll hold it in my office, but if it gets a little crowded, then I'll see if I can find a room. Alphas, by the way, it's Cardwell 250. All right, so let's talk a little bit. We didn't quite finish up what we were doing last week, so I want to start there. We had this theorem that we were working through. And let's recall what it was. So our idea was we had this formula, this recursive formula for the determinant. And that was great, but for large matrices, it might be a little cumbersome. So the idea was to kind of replace that definition with a statement that there was one function that satisfied these properties 1, 2, and 3 that existed. It's not like a figment of our imagination. And that was going to equal the determinant. In other words, our formula would give us this function. But we understood its properties. And where we left off in the proof of this was that we had showed last time that if A is a matrix, and by a matrix, a square matrix, and E was an elementary matrix, then I took this delta function, whatever it is, a product of E and A, I'll get delta of E times delta of A. And furthermore, we could, based on what type of elementary matrix we had, we knew what delta E was. So it wasn't like some mysterious thing. It was a particular number that was determined by what kind of matrix. So this is one thing we should put. Another thing we should put with this, we also showed that if A has a row, this was our lemma, one of our parts of our lemma last time, with all zeros, then this delta function, whatever it is, of A is 0, based on, we showed this using row linearity, property 2. Now what I want to do is I want to kind of finish up this, the uniqueness part of the proof, and say, okay, well, that means that we know that there's only one function, delta, that satisfies the problem. So now let's fix a square matrix A. So fixing A, we are one of two cases. Case 1, A is invertible. If A is invertible, what do we know about A? Based on what we did last Wednesday. Invertible matrices, what did we learn about?
It can be composed of elementary row operations or like the elementary.
That's right. If we do row reduction, right, hit it with a bunch of well chosen elementary matrices, then we'll get to the identity. And then if we kind of take the inverses of those elementary matrices and multiplying that equation on both sides, we'll see that in fact A is a product of elementary matrices. That's one of the things we learned last week. So if A is invertible, then A is going to be equal to a product of elementary matrices, let's say E1 through ER. That means that if I take delta of both sides, well, we get delta of both sides. But based on what we did last time, we see that we can kind of pull off the first elementary matrix. In other words, this is going to be delta of E1 times the delta of the other product. Then we can pull off the second elementary matrix. We can keep on going, and we can see that delta of this product is in fact the product of the delta values. But as I said just a moment ago, delta of these elementary matrices is determined by the elementary matrix. In other words, if I write down one of the three types of elementary matrices, take delta of it, we know precisely what it is. Okay. So this is saying that if we are an invertible matrix, there's no choice about what delta is. It has to be this product of these, the values of the elementary matrices. This determines delta A. That's if A is invertible. In the other cases, A is not invertible. Certainly, there are non-invertible matrices. In this case, if we do row reduction, what can you tell me about the row echelon form of the matrix that we'll end up with? And I'll just say performing row reduction. You'll get you. Well, I'll kind of do some opposite. I'll say, okay, I hit it with E1 first and then E2 and so on. I get something in row echelon form, say A prime. What can you tell me about A prime? Anybody? Yeah.
Does that mean that it's going to have like a zero row at the bottom?
Right. It'll have to have a bunch of zeros on the bottom row. Okay, we don't know about the other rows, but we know that the bottom row will have to be all zeros. Because if it wasn't, it would have a pivot in the bottom row. But it's a square matrix, and we have that staircase. So that would mean that that pivot would have to be in that, entry and column, and kind of going back upwards. You could see that all of the whole diagonal would have to be one when you have the identity. So if it's not invertible, when we look at this row echelon form, we're going to have a row with all zero entries. A prime, I'll just say that A prime has a row with zero entries. It's the bottom row, but okay. But then we know again from last time that delta of A prime is 0. So we get 0 is equal to delta of A prime is equal to delta, this big nasty product. And then again, we can do this factoring. We can kind of take delta of a product, this product of deltas. At least with elementary matrices. But these guys, last time we saw what the values of these were, and they were always non-zero. Plus or minus 1, it's -1 if we have the type 1 where we switch rows. It was the constant C if we multiply a row by C. But remember the elementary matrices, multiplying a row by C, C always has to be non-zero. Okay. And then the third type where you add a multiple of a row to another row, that had delta 1. These are all non-zero, and we can divide by them. And just see that, in fact, delta of A is 0. This tells us that there's only one function, right, that will do the job. If it's invertible, then it has to be the product of these values that we understand for some factorization of A. If it's not, then delta is 0. That's fully determined. And as I said last time, and if you haven't already, read through this section. You can where he shows, it's about a page long, I think, that the recursive formula works. In other words, the recursive formula satisfies these three properties, so it will indeed fit the bill. Now, in the process of proving this, we learned a couple of things, and let me just state these as corollaries. Corollaries are like propositions, but they come after a theorem, right? They're something that follows from the theorem or from proof of the theorem. Statement of that type. This is a very important corollary, which says that if a square matrix A is invertible, I'll just, we're talking about square matrices here, if and only if the determinant of A is non-zero. But there's a very quick test, as long as you can calculate the determinant, to see whether or not a matrix is invertible. Moreover, there is, of course, a formula for the determinant. Not equal, yeah, sorry. There's a formula for the inverse of a matrix using the determinant and the cofactors. You just, so maybe I can write it out. But this kind of follows from something we do later. A inverse is going to equal 1 over the determinant, and this is something you can, I'm sure you've learned in calculus, or in matrix algebra, but you just put the cofactors, or if you want the a minor with the sign, they go m11 here, negative m2, m plus or minus, and it's m 21 m plus or minus. You alternate the signs based on it's -1 to the sum of I and j. But I'm just not going to. So you can, there's a formula if you have the determinant, but of course this formula is not, the fastest way necessarily to get your inverse, because it's going to take a lot of determinant. Yeah. But what you'll notice, of course, is that there's this fraction in front, right? So if this is non-zero, or if this is 0, this fraction isn't making sense, and indeed there is no inverse. Another corollary, which we get from the proof, which is also very important, is that, and this holds for any matrices, not just invertible ones. If I take a product, any square matrices, so if A and B are square matrices of the same size, and the determinant of their product is the product of the determinant. Very, very useful thing to know. And okay, the proof of that, let me just say, I'm not going to prove each. I mean, the proof of this, if they're both invertible, then, they're both able to be written by products of elementary matrices. And so you can just use those factorizations to see that this is going to be true, because we know with elementary matrices, this does hold based on the proof. If one of them is not invertible, then their product is not. That's I'll leave that as an exercise. And then finally, well, there's another corollary, and I'll bring this one over from the book, and we'll see how much we want to talk about it before moving on to the next. So this is just another feature. So you can see, so maybe we'll look at, let's do A, and then I'll say a word about 3. So here's a basic proof of A. Proof for A would just be, so how do you know? You basically is saying the inverse can be taken out of the determinant. In other words, if you have an invertible matrix, you can pull the inverse out. Determinant of A inverse is 1 over the determinant of A. But this just follows because by property 1, we know that 1 is equal to the determinant of the identity, which is equal to the determinant of A times A inverse. Identity is A times A inverse. And then using this last corollary I mentioned, this is determinant of A times determinant of A inverse. Right? So then dividing both sides by determinant of A, you get this equality here. And then for C, Well, okay, for D, maybe I should say for B, it's not hard to see that the transpose of the determinant of a transpose is equal to the determinant of that original matrix. And the reason is that if you take a transpose, maybe I have to just mention quickly. So A is not invertible as transpose is not invertible. So they're both at 0. But if A is invertible, it's a product of elementary matrices. And then its transpose is a product of, in the opposite order, the transposes of these elementary matrices. But if you look at those formulas we had for elementary matrices, for the determinants of them, they're the same. In other words, the determinant of the transpose of an elementary matrix is the same as the determinant of that original elementary matrix. That's not hard. I mean, just think, if you take the transpose of a type 1, where you're switching 2 rows, it's equal to its transpose. So the determinant is the same. If you take a transpose of multiplying a row by a number, again, it's the same. The only one that changes is adding the j multiple of the jth column to the ith column, or a multiple of the jth row to the ith row. It just switches the I and j there. But they both have determinant 1. So the determinants don't change. So this is using this fact and the fact that these elementary matrices are going to have the same determinants you get. But then B allows you to say something like C, because what transposes do is they'll exchange rows for columns. They turn rows into columns. So then you can start saying things about column linearity with determinant and so on. B follows. Again, you can read about this in your book if you'd like. Okay, so what I want to do though now is I want to kind of move on. We will be using determinants. I mean, determinants are a very important invariant, something that we get from a matrix. Learn a little bit about a matrix. Geometrically, as I said earlier on, they give you a sense of the volume of the sort of object spanned by the rows or by the columns, if you will. But right now, I'm going to kind of move into sort of what is indeed a separate sort of subtopic, but we want to use it. We'll come back to determinants after this and use what we learn about permutations to get a different formula, which is I think you probably haven't seen before, or well, maybe you have. I don't know. You guys will tell me. This is section 1.5, and this is a useful section. This is not just something we want to learn for matrices and determinants. It's something we'll use later on when we talk about group theory. A little bit about group theory. All right, so this is about permutations. Does anyone know what a permutation is? Okay. Want to enlighten their fellow students? Yeah. Outcomes. So a set of all possible outcomes of a given set. Is that what you said? So I mean, I think you know what you're talking about here, but I would use a slightly different words. So I would say instead of outcomes, I would say bijections. Or bijective functions. So let me. But I like that you're saying of a given set instead of just numbers. So I'll just say it this way. So a permutation is on a set S, pardon me, is bijective function. If you're worried, don't worry. It's called P from S. Okay, so what does it mean? What is a bijective function? Anyone know? Who knows what a bijective function is? Okay. Who knows what a function is? Okay. That's that. I don't know what a function is. A function, So actually, who does know what a function is? That's a good question. Maybe you guys. So what is a function? Someone, yeah.
You got an input to get an output,
Okay.
and it manipulates the input to the output.
Okay, that's true. That's true, and that's the right thing to think. But it's not the mathematical definition of a function. So who knows the mathematical definition of a function?
Doesn't it map a set onto another set?
Yeah, but what is a map? You replace function with map. So you mean you like get out a map? You like
For every element in one set, it has an element that's different.
you're getting really closer now. So actually, a function in math is what's known as a relation of a particular type. And a relation is a subset of the product of two sets. In other words, so if I have a set, let's say I have a set S and a set T, these are just a collection of elements, right? We say, F is a function from say S to T. What it means mathematically is that in fact, F is a subset of the product set S cross T. This is the product of tuples, right? One from S, one from T. In fact, mathematicians, like in the actual definition, define functions as their graphs in a sense. But then once they're not, it's not any subset. It has to satisfy the condition you're talking about. Namely, it's like the what do you call it? Horizontal line test. It has to satisfy, but of course there are no lines here. It's just sets. They could be, cups of coffee or something. My head went to that. But, so, they can be anything. It's abstract, but it says for every element of S, there exists one pair, exactly one pair. S comma T in this subset. Yes.
That, when you said that it contains exactly one pair, is that what bijective means?
That's what the definition of a function means. Now we're going to get to bijective. Okay, so the bijective is sort of the opposite. Now it says it for T as well. So bijective is saying, okay, so let's talk about this. Let's talk about this because maybe it's not certainly not in the prerequisites to know about some basic set theory, but so let's say some things. Okay, this is an aside on basic set theory. And we're going to do some more of this in the sense that we're going to need to talk about partitions and equivalence relations next chapter. So there's some basic set theory. This stuff is really, it's really elementary, but it's also really important, very important for mathematics. So here I have two sets. Okay, so let me define what a function is in a mathematical sense. This is a function. It's a function if for any S in S, people know this notation? Lowercase s is an element of S. There exists unique pair S comma T in this in F in this subset. Here we say T is equal to F of S. In other words, this is the graph, right, of this. That's what it means to be a function. So now there's two special like properties of functions that we might be interested in having here. So one property is called injective or one-to-one. You know one-to-one probably. But if you want to sound fancy, you can say injective. Your choice. One-to-one says that if I take two elements out of my set S, they go to two different elements. They go to two different elements in T. F is 1 to 1. I'll write it out, 1 to 1. If f of S1 equaling f of S2 implies S1 is S2. In other words, if they were different, their values have to be different. If they have the same value, they must be the same. That's 1 to 1. The other one is onto or surjective, other property. So here we say f is onto if for any element t of t, there is at least one element of S such that I put it into F, the assignment I get is this particular T. Okay. Now, bijective is saying that just that it's both 1 to 1 and onto. So 1 to 1 correspondence bijective this guy is both, F is both 1 to 1 or injective insertion. Okay. Now it turns out this is equivalent to another. There's another description of being bijective. So this is equivalent to the existence of a left and right inverse. In other words, when I say left and right, I mean, it's the same thing. Now, what do I mean by that? We talked a little bit about, we talked about invertible matrices, right? Talked about invertible guys, but there was this, what was the operation we were using when we talked about invertible matrices? We're talking about matrix multiplication, right? Here we're talking about functions. What does it mean for a function to have an inverse? Well, I need the operation. And the operation that I'm talking about here is composition of functions. I'm composing functions. And what's the identity function that we have in mind here? The identity function is just that function from a set to itself that sends every element to itself. Okay. So this property of having a left and right inverse, F inverse, in fact, it's a little bit more complicated. We have two different sets, right? We have a function f from S to t, and the inverse will then go in the opposite direction. And the point is when I compose them, in other words, if I take f inverse of f, this is the identity on S, and then if I take the opposite f composed with f inverse, this is the identity on t. Remember, when you're composing functions, you kind of go from the right to the left. Functions are Jewish or something. So,
Talk through those last two equations.
huh?
I was writing stuff.
Yeah. So the idea is, okay, so if I'm going, so I can think of S to T. I'm saying that I have some function f inverse, and when I compose them, so in other words, I first hit an element with f, and then I hit it with f inverse. This is f inverse. The way it's written is this way, sort of reverses the. This guy has to equal just the identity on f. inverse, which means that it sends each element to itself. That's what it means to have for F to be an inverse, a left inverse, and then F inverse to be a left inverse. But then you can go the other way as well. You can say, okay, well, let's start here with this left inverse, and it should be also a right inverse. I mean, functions can have left inverses without having right inverses. They can have right inverses without having left inverses. But if they are bijective functions, they have a single function that does both. So that I'm going to leave as an exercise for you guys when you want. But it's actually fairly important. Maybe we'll come back to it. I'm not sure, but this equivalence is important. So, and it's important in the sense that when we look back at our definition of permutations, well, a permutation is a bijective function from a set to itself. So that means it will have an inverse permutation.
The original set.
Well, there's and for permutations, we don't have a T, right? We have a single set all the time, and they're just functions from that set to itself, but they're bijective. But then as the idea of having an inverse is saying sort of undo whatever that function does by composing with some inverse function. Okay, so now this is very abstract, but so what we want to narrow it down and kind of be talking about something a little more concrete as we go. So what we're going to do is we're going to look at a particular set, a particular type of set. So we'll take this notation, little notation here. So taking S, our set that we're interested in here, to equal set 1 to just the positive integers going all the way up to the letter n, or the number n, I should say. We write S sub n as a set of permutations. These are the set of bijective functions on this set 1 through n. There are other notations. Sometimes people will write a sigma n, and then there's also this sort of like Greek. I'm not going to try to do it. Some kind of, well, here I go trying to do it. Some kind of Greek like G sub n. I don't know. It's like combinatorics people write G sub n now. I don't know why. Someone started the trend. But sigma n you'll see, and if you do read enough math, S of n is pretty standard too. As we'll see later on, this is something called the symmetric group. There's a mathematical structure we're going to study called groups, and this will be the set that is underlying the symmetric group. So now, sorry, question. Now, there's a common way of writing a permutation, writing out a permutation, which has its problems, but Arden actually spends like seems to spend like a paragraph kind of saying how awful it is. I love that. You know, he's got a problem with this notation. So, but it's pretty common. You're going to see it in, if you run these permutations. So let's talk about it. So usually, let's say n is 4 or something. Okay, what people will sometimes do is they'll do the following thing. They'll write a permutation like this. And the idea is you're just writing the assignment. So you're saying 1 is sent to 3, 2 is sent to 4, 3 is sent to 1, and 4 is sent to 2. Okay. This is like a way of denoting a permutation. Saying, okay, you're just saying where everything goes. Is it clear? I'm not seeing any nodding heads. That's scary. Is it okay? It's a bijection, right? All the numbers up here, all of the numbers 1 through 4 are listed here. Right? And so we're imagining this as a function. But Arden doesn't like this. For and he gives a reason. I don't think it's not a bad reason. There's another way you can denote permutations. It's actually mathematically much superior. That is true. So it's so much better, right? I mean, but you know, we're not all going to be mathematicians. Except for you guys, you're all. And it's called cycle notation. Instead, cycle notation. And it's pretty intuitive what's going on here, but let's give an example. So let's say I do 2, 4, 1. I'm going to show you this by example. Here's an example. 2, 4, 1. So this is a 3 cycle. And it's a 3 cycle because there are 3 numbers. There's not 241. I'm thinking of them as 3 distinct numbers. And what it's telling me is it's telling me this notation for a particular permutation. And that permutation is the following thing. It goes left to right, and it takes 2 to 4. It'll take 4 to 1, and it'll take 1 back to the beginning to 2. So there's like just a little picture here that's drawn in the book, which is fine. What does permutations doing? And you may see or observe, I left out one of my friends here, like 3, right? 3 is not in there. So the question is, what happens to 3? Well, if it's not in there, 3 just goes to itself. 3 is going to go to itself. You could have a 1 cycle and just write 3 if you wanted, but that's almost never written. So, is it clear? I mean, it's not super hard, right? But it's just maybe it takes a little getting used to. So let's take a look at this permutation I wrote up here, and let's see if we can write down cycle notation. Now, not all permutations are cycles, right? They're products of cycles with different numbers. You can always do that. Let's see about this one. So if I want to write this in cycle notation, I just kind of ask where things go, and I follow it along. So I'll start with 1, and I'll say, okay, well, 1 goes to 3. Now 3, it goes back to 1, right? When I look here, it goes back to 1. I'm done with my cycle there. But I'm not done with all my numbers. So I look at 2 and I ask where 2 is going. And 2 goes to 4, and 4 goes back to 2. So this is a product of two cycles. This permutation. This is the notation. It's a little superior in that it's, you know, more compact way of writing the permutation. But it's also easier to manipulate, I would say. So that's its main advantage. And it actually tells you a lot more about permutation here. Okay. By the way, there's some vocabulary. One, we can say a K cycle is cycle of form just with K numbers in it. I'll just write it this way: I1, I2, IK. That's a K cycle. So another word for 2 cycle is a transposition. That's you're sort of transposing, I mean, you're in the English sense of the word, you're transposing 2 numbers. I'll often call, I won't usually say 2 cycle, I'll say transposition. And then, of course, there is an operation on permutations. We can take 2 permutations and compose them. That will still be a permutation, and you can see, you can prove that easily by that relationship between having an inverse and being a permutation. But you have to be a little, again, you have to be a little sensitive about which direction you're composing. Okay. So in other words, you want to think of these as functions. You want to think of these permutations as being functions. So let's do an example of composition. Make sure that we're comfortable. So let's say 1. I could look at something like, well, actually, let me just give you one example. Let's say I'm composing a 3-cycle 1-3-2 with a 2-cycle transposition 2-4. Okay. Usually you don't write the little circle for composition. You'll just write it as a product, essentially. But there, you should think of it as being composition. Now, what you want to do is you want to start. You're starting on the right. In other words, this is absorbing this as a function. There's some number here, and this function is saying do something to this number, and then you perform that function on whatever you get. So you go from the right to the left. So if I start with 1, I have to ask, okay, what does this transposition do to 1? It does nothing, right? This guy doesn't do touch 1. So nothing happens there. And then this permutation will send 1 to 3. 1 goes to 3. Okay, now I have to ask where 3 goes. And again, the first transposition does nothing to 3. So I just need to look at the second transposition, the second cycle, and it sends 3 to 2. But now I have to ask where 2 goes, and 2 by the first transposition, this first cycle goes to 4, and then 4, nothing happens here. Oh, thanks. Oops, I don't want to block that. So now, where does 4 go? Well, let's just double check. We know that 4 is going to be sent to 2, the first one, and the second one is going to send 2 to 1. So 4 will go to 1. Indeed, I can kind of close off my cycle. I get a 4 cycle. 4 is going to 1. Clear?
So,
yeah.
In the top part, you did the same notation, but there's no connectivity. So if you just leave those separate, you can only compose them really if they both
This
share.
part here,
Yeah.
the top part here.
When you wrote the 1, 3, 2, 4, not the 1, 3, 2, 4. Yeah, that.
This guy.
Yeah.
Yeah. So this way of writing it, we're not going to use this really, but I
I'm
wanted
talking
to.
about like you have 1, 3, 2, 4. Are you still
that's-
composing them?
It is a composition. It's a good point. So these two, let me add a little vocab here too. So these guys are not what we would call disjoint cycles. If I look, there's this common number in both of them, right? And what I want to do if I see a common number is I want to actually compose, because I may end up breaking up those cycles. Maybe it'll kind of give you a different picture. However, up here, as you noticed, we do have 2. Like, why didn't we compose these? Well, because these are what are known as disjoint. They're disjoint cycles. Their numbers are all, there's no shared number between them. There's no intersection. So there we have to write them separately. But you'll notice that in fact, these two commute, which function composition certainly does not commute, but these guys do commute. It doesn't matter which order you write them. So if you have disjoint cycles, you don't have to worry about the order in which you're writing. But if they're not disjoint, you very much need to worry about it. They will not commute. We could check that. Let's check that. If we did this, what would we get? Well, 1 will still go to 3. 3 will now go to 2, but 2 goes to 4. And 4 will go to 2. And 2 will then come 1, and that'll be it. But you'll notice that these two are definitely different. They're not equal because, for example, 3 goes to 4 in one, and 3 goes to 2 in the other. So this one, 3 is going to go, I start on the right-hand side. So 3 is going to get sent to 2, and then 2 is going to get sent to 4. So I have to kind of, I'm composing functions. This function will send 3 to 2. This function will send 2 to 4. So I first send 3 to 2, then I send 2 to 4. So 3 as a composition is going to go to 4. It's a composition of functions. Composition of functions means, okay, so let me be a little more clear. So if I have F composed with G and I put in X, maybe something from calculus. This is equal to F of G of X. That's a composition. But here I think of this as G. This is F. So if I take 1, 3, 2, 2, 4, think of it as a function. Sorry about all the parentheses. And I'm asking where 3 goes. Well, this guy, this is my G, right? This sends it to 2, 4 of 2. And now 2, 4 of 2 sending it to is equal to 4. Okay, sorry. I mean, this is very sloppy, but hopefully it gives you a sense. All right, so there's a little bit more from this section. We'll cover it on Wednesday, but do read through the rest of the section if you could and make it go a little faster. And I have office hours today. Otherwise, we'll have some stuff on Friday. Homework, please. If you haven't already submitted it online on Canvas at some point today. I'm going to be a little forgiving with the first homework. It's a little late. That's fine for the first one, but let's try to get on schedule after this. Okay.
So you still have an office hour right after this?
I have office hours now.